Assalamualaikum and good evening. Think about this moment. Talent is everywhere, but opportunity is not. Our mission is to bridge that exact gap. We inspire and prepare the next generation for the future by making robotic engineering and STEM accessibility for every student. What is STEM? STEM is stand for science, technology, engineering, and mathematics. So through hands-on workshop and competitive events, we aren't just teaching the technical skills. We are cultivating a community of problem solvers. We provide the tools so that this student can turn their boldest idea into reality and confidently tackle the complex challenge of tomorrow.
Okay. And now I will continue to the website concept. Firstly is educational path and buildings. The primary headline, learn to code, build and automate with Arduino, establish the platform as a learning hub. The content is structured around a sequential learning path designed to take students from a basic level to a high level. It targets learners who want to bridge the gap between software and hardware. The second one is practical e-commerce integration. Rather than just providing theoretical tutorials, the website integrates hardware distribution. Under the kit and product menu and the homepage call to action, it provides complete toolkits, robot chassis, sensors, and project bundles. This suggests a hands-on learning model where users can buy the physical components needed to complete the outline modules. And the last one is academic and community engagement. The platform features a distinct section dedicated to UTEM STEM activities, indicating a collaboration, partnership, or project route linked to University Technical Malaysia Melaka (UTEM). This adds an academic framework to the site, focusing on community outreach programs, school or university robotics club, and mini robotic challenge and competition aligned with industry standard.
Okay, now that you know our mission, now let's talk about how we bring that initiative to life. We follow a structure, six-step deployment process to ensure our STEM resources are high quality, functional and impactful. First step is research planning. We begin by mapping at our STEM curriculum and identify our specific target audience to ensure the content meets their exact needs. The second step is design mockups. The next, we move into UI or UX wireframing, establishing a cohesive tech team that make the learning experience engaging and intuitive. The step 3 is platform setup. From there, we build the core digital infrastructure, configuring our Wix environment and managing that back-end database integration. Step 4 is content integration. Once the platform is ready, we populate it by uploading our specialized STEM modules and supporting interactive media. Step 5 is testing and debugging. So before anything goes live, we run through a quality check, focusing on rigorous functionally testing and strict link validation. Step 6 is accessibility and adjustments. Finally, we optimize the entire platform for accessibility, making final adjustment to ensure deployment is seamless for every single student. This meticulous pipeline is how we scale our ready and confidently deliver the future of STEM education. That's all. Thank you.
And now we moving to platform and structure. We use the Wix platform builder that's powered by Wix to deliver a fast, secure, and interactive learning experience. By using this platform, we can use smart design tools instead of complex coding.
We seamlessly combine the STEM modules, booking system, and rich media into the professional accreditation platform. Sitemap and our user journey can be used for centralize a mega menu to group content into a 4 easy STEAM robotic, coding, electronic, and resources. The intuitive design given student, educator, and parents quick access to everything from the course to community form. And you can see that the picture show the guideline for the website usable.
Now, let's dive into our first core topic, Arduino and robotic. When we talk about introducing robotic into the academic landscape, we need to platform that balance power with accessibility. That is exactly where Arduino shine. Why Arduino at school and university? If we look at why Arduino is the go-to standard for school and universities, it really boils down to 4 key advantages. First, low startup cost. Hardware should not break the bank. Arduino boards and their components are highly affordable, making them incredibly accessible for educational institutions looking to deploy them at scale. Second, it's easy to understand. It utilizes a simplified C or C++ based programming language. This means students don't get bogged down by overly complex syntax right away. They can focus on the logic of building. Third, a very large community. You are never on your own. There are massive amount of shared documentation, pre-written code, libraries, and active forums out there to help students troubleshoot instantly. And fourth, improving STEM skill. It bridges theory and practice by perfectly combining elements of science, technology, engineering, and mathematics in a practical hands-on way. Microcontroller board comparison. But education is one fits all, and neither is hardware. Arduino provide a scalable microcontroller comparison to fit different project needs. As you can see here, we typically start with the entry-level Arduino Uno, which is the gold standard for beginners. It features at Mega 32.8p microcontroller and operates at 16 MHz, making it perfect for basic project, electronic wiring exercise, and foundational beginner learning. However, as student project grow in complexity, the platform scales up easily to more advanced board like the Mega or ESP32 variant for complex robotic IoT application. Ultimately, Arduino serves as an affordable open source gateway that takes students all the way from learning how to blink a simple LED to building complex autonomous robotic system. Moving on to module page, let's look at the actual learning curriculum. What we have built here is true step-by-step robotics pathway. It is designed to scale dynamically starting from foundational hardware and mechanics for absolute beginner using Arduino Uno, moving into intermediate wireless system integration, and finally peaking at advanced AI and IoT-driven autonomous engineering tailored for university-level innovator. Let's break down this curriculum truly block by block to understand how a student progress from zero to advanced robotic engineering. Okay, number 1, LED blinking and digital output. Every great journey starts with a single step and an end in robotic. That step is mastering digital signal. In this first block, students dive into LED blinking and digital output. They learn the mechanic of digital pins, specifically understand how high and low signal dictate binary logic. They get hands-on with fundamental code function like pin mode, digital write, and delay. By creating single and multiple LED blinking pattern and eventually building full traffic light simulation, students master basic program logic, timing and sequencing, and physical circuit assembly using breadboard. Once they understand visual output, we introduce audio feedback via buzzer and sound generation. Here, students work with both active and passive buzzer. They learn how to generate tones using tone function to create simple melodies and alarm. The core engineering value here is shifting from static code to event-driven audio feedback. This develop vital skill in digital output control, frequency and timing concept, and introduce them to event-driven programming structures. Move to the top right card. Next, we bring things to life with physical motion through servo and motor integration. This is where students transition from pure electronics to kinetic robotics. They learn DC motor speed control using pulse width modulation or PWM alongside precise servo motor positioning, motor driver fundamental, and multi-motor coordination. To put this into practice, students tackle example project like a robotic arm and automatic gate system or pan and tilt camera platform. The skills developed here are crucial for actuator control, motion planning basic, and mechanical integration. Drop down to the bottom left card. Now that the student can move hardware and emit signal, they need a way to read data natively. This brings us to LCD and data visualization. Students learn to display real-time and sensor data on 16 by 2 LCD screen utilizing 12C communication protocol as well as working with Crisp OLED display. They move beyond basic automation into human-machine interaction by designing user interface and custom menu system controlled by physical button. This teach them real-time monitoring and professional data presentation. Move to the bottom center card. Next, we take the robot and connect into the wider world with IoT robotics. This bridge local hardware with cloud environment. Students learn how to connect their robots to cloud platform for real-time data, monitoring, and remote control through web and mobile application. Leveraging powerful protocol like MQTT and REST APIs, they got exposed to prominent platforms such as Arduino IoT Cloud, Blink, and Node-RED. Through this, they develop highly industry relevant skills in cloud computing, remote monitoring, and data analytics. Finally, we reach to the apex of the pathway, autonomous navigation. This way, true university-level innovation happens. Students move away from pre-programmed paths and delve into high-level robotic concepts like SLAM, simultaneous localization and mapping, sensor fusion technique, advanced path planning algorithm, and obstacle mapping and avoidance. And they integrate cutting-edge industrial technology including LiDAR, IMU system, GPS model, and ROS, the robot operating system. By the end of this module, students aren't just building gadgets, they are engineering fully autonomous robotics capable of real-time decision making and navigation in unpredictable environment. As you can see, this module is carefully structured in ensure that no matter a student's starting point, they are systematically guided by flashing a simple light bulb to develop a fully cognitive, cloud-connected autonomous system. Thank you.
And then we have a kit product for a planner is used to good to as a what you put inside it. Introduce the product kit. Monetize and productive superpower is a premium and ready to use bundle of the digital asset that think a pre-made video template, script outline, design element, and SEO checklist. Instead of the building from the scratch, user can buy and unlock specialist kit tailored to their specific niche. Moving on the digital store form of our project, the website design is cutting edge AI tools and content ecosystem. Our web design could be look just good. It has a feel intuitively, lightning fast and deeply integrate. We choose a high contrast white, charcoal and neon green visual language. The white represent clarify and cleanliness,
while the Neo Green acts a digital plus, guiding the user I directly to high value action, converting the casual visitor into the active character.
For multimedia element, next is the UTEM STEM page. The text on this page explains the purpose of the UTEM STEM platform, which is to contact with the community and promote STEM education. It highlights how the university share knowledge in robotic, drone, and microelectronics through mentorship program, workshop, and competition. The text provides users with a clear understanding of the platform role and objective. Moving on to the gallery page, the text describes the gallery as a visual portfolio that showcases STEM activities and achievements. It explains that galleries serve as a proof impact by displaying workshop, demonstration, and student engagement. The information helps users understand the purpose of the gallery and the value of the activity being presented. Lastly, for testimonial, page content takes the highlight and feedback and success story from the student and the educator. The content emphasizes building trust, showcasing real-world impact, and demonstration the value of STEM program. Through this testimonial, user can gain insight into participant experience and benefit they receive from the activity.
Okay, so for work group reflection is where we work together to build this website. So operating robostemhub.com present unique challenge and substantial growth opportunities. Coordinating STEM curriculum across diverse age groups require a shift from general tasks to structured delegation among team members. We overcome critical logistical and development hurdles by implementing digital collaboration tools, enabling remote circuit simulation, and a real-time code reviews that align all contribution with our vision for accessible technical education. Finding the balance between deep technical functionality such as intricate sensor integration and aesthetic user interface design taught us to prioritize a cohesive platform that maximizes educational impact and visual clarity. And lastly, in conclusion, RoboSTEM Hub functions as a comprehensive hands-on EdTech ecosystem that seamlessly integrates structured Arduino learning pad, physical robotic kits, and academic community initiative to empower the next generation of coders and engineers by providing learners with an end-to-end framework from purchasing the necessary hardware to progressing through beginner and advanced modules. The website transforms traditional STEM education into an interactive, accessible experience. Furthermore, its unique collaboration with UTEM reinforces its academic credibility, establishing the platform not just as a static tutorial site, but as an active hub for grassroots community engagement, robotics club, and industry standard competition. That's it for us. Thank you.